So grounding is just connecting one part of your circuit to the earth or some large metal object. So for instance, in a car, you ground to the chassis. Okay? In a house, you ground to the ground because you have that option. In a car, why do you not ground to the ground?
Because then you can't move.
Yeah, it makes it really hard to drive the car away. So there's some logistical considerations to keep in mind. But basically, remember, any large conductor is going to take any excess charge, okay? So the chassis of a car works pretty effectively as the ground, although the ground is the most effective because Earth is really a large conductor in some ways. So, it can pretty much sustain any amount of charge you can throw in there. Okay, but what does that mean practically? Well, if we look at this circuit, right, just based on what we know about circuit analysis, this is 10 volts. This gives us about an equivalent resistance of 20 ohms. That means it's about a half an amp going through this series circuit, which means this is about 4 volts, 6 volts, you have 10, minus 4, minus 6 gives you 0. Okay, all that works. Will grounding change any of that? Does grounding affect the way circuits function? Not really. Okay, so it turns out under normal circumstances, unless you have some weird grounding error, okay, unless you use 2 different grounds, which is something that could happen. There's a reason in the lab I said you have to ground the battery to the power supply, right? They have to have the same ground. Because if you don't, you get really weird answers because the battery isn't grounded, so it can float at some other potential, okay? So for instance, if you touch the doorknob on a dry day and you get shocked, you touch your car on a dry day and get shocked, that's not alarming. But if you come into a building like this and get shocked every day by the same thing, that's probably a grounding issue. And the reason we have grounding is extra charge can build up on things and it never goes away unless somebody touches it. And you don't want to be the person who touches it if it's a lot of extra charge, because then you are the ground, because you are standing on the ground. You are the fastest way to conduct that extra charge to the ground. Okay? So, grounding is more of a safety issue. It does not change the function of circuits. Okay? It doesn't matter for the circuits. What it matters for is you not getting electrocuted when extra charge builds up. All right? So under normal conditions, does not affect the operation of the circuit. So all the things we learned, you should still do those in problems with grounding. Okay? Resistors still add the same way. Loop and junction laws still work the same way. Analyze the circuit the way you've been analyzing it before dealing with the ground. Okay? Yes? Okay. So the main difference is, this is the ground symbol. Look, we know the voltage difference across this is 10. The voltage difference across this is 4. And the voltage difference across this is 6. What we didn't know before is what the potential, if I just asked you for the potential here, and there's no ground, let's go back actually. Without ground, you can't really tell me what that is. You can tell me it's 10 more than here, okay? But if this is, so it could be any potential, because if there's floating charge, right, remember, potential is just summing up the charge. So if there's extra charge, you could start at 2, okay? And then when you add 10, you're at 12. As long as the difference is 10, the circuit still works, okay? What ground does is it tells us where 0 is, because it's hooked up to the ground, and therefore it has to be 0 because any extra charge at this point goes to the ground. Okay? So now this is 0. So when you go through here, what's your potential here?
10.
10, because the potential difference is 10. Then you go through here, what's your potential here?
6.
4. Yeah, 10 minus 4 is 6.
Yeah.
Okay? Then down here, 6 minus 6, you're back to 0. All right? So there's a difference between the potential difference, right? This is a 10-volt potential difference, and the potential at a point, okay? It's the difference between V and delta V, okay? This would be like V initial and V final versus delta V. So without the ground, you could And then this would be 20 minus 4, which would be 16. And then this would be 16 minus 6, which would be 10. Right? That still works. The circuit would still work the same. But the ground tells you where 0 is. So now you can find the absolute potentials, not just the potential differences, right? All this stuff, all these voltages, these all represent potential differences, okay? This says the difference between here and here is 12 volts. It doesn't tell you what the potential is here and what the potential is here. All it tells you is we know if the potential here is 10, then the potential here is
2.
negative 2.
Oh.
Okay? It would be 10 minus 12. All right? So potential difference tells you the difference between the 2 points. Point potential, or absolute potential, tells you the potential at a point. Now, that's not as useful a thing to know as the potential difference, but it is a real thing you can know. Okay? So, for instance, right, if you want to find the point potentials, those are different. Now, it's easy if you ground the negative terminal of the battery, but you can ground other parts. Okay? This is the standard place to put the ground. That doesn't mean it's the only place you can put the ground. It's where you should put the ground, but it still will work if you ground somewhere else. Okay, so I just want to explore that for a second. I want to take a picture. Sorry, I'll totally erase something. So let's try putting the ground somewhere else. Okay, so here's our circuit. So this is 10 volts. This is
8 and 12.
8 and 12 ohms. So this is potential difference is 4 volts. Potential difference is 6 volts. Okay, if we ground it here, it looks like that, right? So that means all of this stuff connected to ground has to be 0. Everything from here to here has to be 10. Everything in here is 6. All right, let's do something weird. Okay, now our ground's here. What's the potential here?
0.
0. What's the potential here?
Negative 10.
Oh,
Negative 6.
What's the potential here?
It's negative 6.
Negative 6. What's the potential here?
4.
4. And then this is also 4. And then as we go through here, it goes down to 0. Okay? So you'll notice the potential difference across each circuit element remains the same no matter where you put the ground. What changes is the point potentials. Okay? And so when you do a grounding problem, you just call wherever the ground is 0 and just count from there using the same sign conventions we did for loop law. Okay? Because if the current's going this way, if we go backwards, right, this should be plus 4. If we go this way, it should be minus 4. Right? Cool. So let's try this out. So it either turns off or stays the same. Okay. What happens to the current when you ground this?
What's the ground? Voltage equals 0.
It's the same, right? The current shouldn't change. All that changes is the relative voltages. Does that matter?
No.
No. all we really care about are the voltage differences, and those are completely unaffected by ground. So this is going to stay exactly the same, okay? It's a weird way to set up a circuit, but it doesn't change the circuit function, right? Why do we ground to the negative terminal of a battery or to the negative side of a power supply?
Potential soon.
It's just convention, okay? If everybody does it differently, that's dangerous. Not because it changes the function of the circuit, but because when you go into someone else's house and redo their wiring and you don't know where the ground is, you don't know where it's safe to touch, okay? So the reason we ground at the way we ground is just convention. There's some minor safety issues, but it doesn't affect the way the circuit works. So technically, you could ground it anywhere, okay? But it's just convention. It's not gospel.
Yeah, going to Chicago.
When doing grounding problems, you want to remember that the ground is sort of what happens after you've already solved the problem. So what we're going to do first is just ignore the ground. And we're going to solve this circuit as though we're not dealing with ground at all. So if we're solving this circuit, we just need the equivalent resistance, which, since this is in series, is just 5 ohms plus 2 ohms plus 3 ohms, which is equal to 10 ohms. And then we just use Ohm's law to figure out what the current is. So delta V equals IR. That becomes I equals delta V over R. Delta V is 20 volts. And R is this 10 ohms we just calculated. So we have a current of 2 amps. And just like before when we were doing Ohm's law and Kirchhoff's law problems, once we have this current, remember this is the current that goes all the way around this series circuit, but we can use the current to figure out for each circuit element delta V. So remember, once again, delta V equals IR. Oops. So remember, once again, delta V equals IR. So we do the current, which is 2 amps, times the resistance, which in this case varies depending on the resistor. So this is going to be 2 times 5, so that's 10 volts. And that's our delta V. Okay, delta V here, actually, I'm going to move it back here. Delta V here is 4 volts, and delta V here is going to be 6 volts. So now we use the same rules that we would use for our loop and junction law, primarily the loop law, once we add ground back in. Now the only thing you have to remember to get started is that the point potential, meaning not the difference in potential, so not delta V, just V, okay, that is going to have to start at 0. So this whole line from here to here to here all the way to here, all of this is going to be 0 volts. All right? Then it depends on which way you're going through the circuit. So if we want to go this way, we pass through this resistor. And are we going with or against the current? Well, we're going in the same direction as the current. So that means if we're traveling the same direction as the current, we're going to subtract our delta V. So this is V, and then we're subtracting delta V. So that's 0. So So this is minus 6 volts. And it's minus 6 volts all the way from here up through here until you reach another circuit element. So both of these points are minus 6 volts. Then we keep going. So once we go through the battery, we're going through in this direction, which is from negative to positive. So that means that since we're going from negative to positive, that is a plus 20. So negative 6, this point potential, plus delta V of 20 volts. So that's going to give us negative 14 volts. And that's negative 14 volts from here all the way to here. Okay? Last but not least, as we go through this resistor, once again we're traveling with the current, so that's going to be minus 10 volts. So oh, that's not minus. Shoot. So once we go through this, we get plus 20 volts, so 6 volts, negative 6 volts. Okay. So since we're going through this battery from negative to positive, that means we add 20 volts. So we start with negative 6 volts plus 20 volts. That gives us 14 volts. And that's going to be true from here all the way to this resistor. Now last but not least, we're going through this 5 ohm resistor. We're going in the same direction as current, so we're going to subtract our delta V. So we take our V plus negative 10 volts, and that's going to give us 4 volts. And it's going to be 4 volts from here all the way to this next resistor. Okay. You could also go around backwards. So if you wanted to travel around the loop the other direction, we use the same rules as loop law. We start at 0 volts, right? All of this is 0 volts. We travel up through this resistor. Because we're going against the current, which is going this way, that means we want our delta V, this thing, to be positive, so that's 4 volts. And then as we travel along here, it stays 4 volts. Then we get to this other resistor. Well, that's going to be plus 10 volts because we're going against current again. That should give you 14 volts. You go backwards through the battery, so that's negative 20 volts. That's negative 6. 14 minus 20 is negative 6. And then since you have negative 6 over here, since you haven't passed through any circuit elements, when you go back through this one, you're once again going against the current, so you get negative 6 plus 6, and that gives you 0 volts.